Okay, so thank you very much for this kind invitation to TSD. This is a very good opportunity for me to know people here in Brno. This talk is entitled Entailment Graph for Text Analytics in the Excitement Project. So actually this is the story of a European project which is called Excitement, which means exploring customer interaction through textual entailment. So it's not I'm kind of a coordinator of this project, but actually this is a joint work with many people, particularly with Ido Dagan from Bar-Ilan University in Israel, with Günter Neumann from the FKI in Saarbrücken and Berlin, and Sebastian Pado from University of Stuttgart. And then behind these people, there are many people who actually have been working for 2 years and a half on this project. So the focus of this talk is on inferences. So this is a very well-known part of understanding natural language. I will focus on a specific kind of inference, which is textual inference. So I'm not going to talk about logical forms and logical deduction. The kind of inference which we are addressing, we call textual inference, because it's a kind of relation between two portions of text, okay? And specifically, the kind of relation we are interested in is entailment. So, of course, there are many other relations, including similarity. Two portions of text, the meaning of two portions of text may share some similarity, or one portion of text may be the cause of another. But our goal for today is entailment, the entailment relation. I will spend a few minutes at the beginning of this talk introducing this area. The second item in the agenda of the talk is technology, which is the available technology for addressing textual inferences. And particularly, I've been involved during the last 10 years in one of the several initiatives around textual inferences, which is recognizing textual entailment, RT. In these initiatives, we built data sets and we asked the system to automatically perform automatic recognition of entailment relations. So we are interested in the state of art in this area. Then I will tell you about one of the results of the Excitement project. We have been developing a platform, an open source platform for textual inference. And this is what I would like to tell you. I would like to briefly to describe the main feature of this platform, which is something that it's available for the community and for researchers interested in textual inferences. The third item of the talk is about one possible application of textual inference. And particularly, we are interested in text exploration. What does it mean? It means that we have documents, we have possible streams of data coming, and we need to provide useful and compact ways to organize such knowledge. The way we suggest is to organize this knowledge around entailment graphs, where you have nodes, where you have statements, portion of text, and the edges in the graph are entailment relations. So I will introduce the general idea of entailment graph in this part of the talk. And finally, I would like to show you how in the Excitement project we are trying to concretely apply this idea of the entailment graph in a particular scenario, which is the analysis of customer interactions. So in this scenario, we have customers calling call centers, either through the telephone, emails, and other ways, and we want to organize the relevant content of the interactions in such entailment graphs, which then are useful to the manager of the call center in order to understand what is going on, which are the main issues raised by customers. Okay, so I will briefly tell you how we are working in this specific scenario. What is important is that we have data sets. Okay, so we have been developing data which are available through anonymization, of course, for research. And then I would like to finally to give some idea of the experiments that we are doing, which provide baseline results. So let's start from the beginning of the story. What is inference? So inference is a process aiming to derive by reasoning or to conclude for premises. So you have 1, 2, 3 premises, and you conclude, and you have one conclusion. So this is a kind of process through which you discover. You are supposed to discover new knowledge, which was not explicitly mentioned in the premises. So this is one example. So you have one premise. Very few Italians speak English well. You may assume that this is true. Premise number 2, Mario is Italian. Sounds quite reasonable, given the name of the person. The conclusion is that Mario does not speak English well. Okay, so we all understand that this conclusion is probable. Okay, so you may think some possible words where this conclusion is not true. Maybe Mario has spent a long period in the States, so actually he speaks English very well. But let me say that this conclusion, many of the people would say that this conclusion is very likely to be true. Okay, so this is the kind of arguments made of premises and conclusion that we are interested to model. Okay, and our suggestion is that actually this kind of reasoning is very frequent when we understand documents. Okay. I told you that we are interested in textual inferences. Okay, so actually we want to infer new textual expression from given ones. Okay, so in this process, basically there are two kinds of knowledge that are involved. The first one is what we call the community usually called extra-linguistic knowledge about the world. Okay, so for instance, if I say it rained yesterday, then we can derive that yesterday was wet. Okay, so with some probability. But this is the knowledge we use to derive this piece of knowledge is knowledge about the world. Okay, so we know that when it rains, then everything is wet. The other kind of knowledge involved in semantic inferences is linguistic knowledge. Okay, so knowledge about the variability of language. So if I say I bought a watch, then I can derive I purchased a watch, because as native speakers of English, we know that the meaning of bought and the meaning of purchase is very similar. Okay, so this is a kind of linguistic knowledge which allow us to draw this kind of inference. So this is the definition that I will be using during this talk, and the definition that has been using in recognizing textual entailment. So this is a directional relation between two text fragments. Let's call them text and hypothesis. This is the terminology used in logics. And the definition is that the text T entails the text H if a human reading the text T will infer that H is most likely to be true. Okay? So first you read the first sentence, then the second, and you judge a kind of probability. Does the probability of the second increase if you know the first? If yes, the probability increases a lot, then the judgment is yes, there is a textual entailment. So let's see few characteristics of this definition. First, it's based on Neumann as a gold standard. Okay? In order to understand whether entailment holds or not between two portions of text, the human judgment is the gold standard. Then there is an assumption about background knowledge. It's not enough the two texts. During the reasoning, we use a lot of background knowledge. So a system which is supposed to mirror this kind of reasoning should have such background knowledge. Another fact is that bidirectional entailment, when T entails H and H entails T, basically corresponds to equivalence, or what we know as paraphrasing. People who have been proposed this framework, recognizing textual entailment, actually had in mind a lot of applications for this, okay? Like in question answering, in information extraction, information retrieval. So let's just look at question answering. So if you have a question like what affects blood pressure, then you may think that the answer is contained in a text fragment, in a usually huge document collection, like salt causes an increase in blood pressure. In order to understand whether a certain candidate answer is correct or not, you may think that it's enough to discover the entailment relation between the affirmative version of the question and the candidate answer. If there is an entailment relation, then this candidate answer is going to be a correct answer for the question. And similarly, it works for information extraction and information retrieval. So actually, this definition of textual entailment as a relation between two portions of text can be used, practically used, in many application scenarios. So there are a number of aspects which makes this definition appealing. Okay? And actually, this textual entailment framework, let's call it this way, during the year has received quite a lot of popularity in the computational linguistics community. So there has been, one of the main initiatives has been the organization of so-called RTE, recognizing textual entailment tasks, okay? So started in 2005, if I'm correct, and went through for many years. So actually now we have a lot of benchmarks where people can do research, and we have systems, results, a lot of experience in this area. Of course, the task is very complex. Judging the entailment relation between two portions of text requires, as I told you, knowledge of the word, knowledge of the language, so it's very complex. And we will see in a moment which is the state of art in this area. What is important is that this definition of text of semantic inference is theory neutral, okay? So it's not that there is a particular theory behind this definition. And actually, this makes it possible to use different approaches. A logical-based approach where you have formulas in, let's say, first-order logics, but you can use also very shallow methods like similarity and so on. We can compare this definition of textual entailment with paraphrase. And as I told you, paraphrase is just bidirectional entailment. With respect to similarity, we think that similarity is not a well-defined relation. So you know that there are initiatives aiming at automatic identification of the similarity between two portions of text. But we think that textual entailment is better defined than similarity. Possible extensions to the notion of textual entailment include contradiction. Basically, contradiction is the other side of the coin, okay? So two portions of text, there is a contradiction relation when two portions of text include information which is incompatible in some sense. Okay, so in this case, he bought this car yesterday, and he bought this car a year ago. I mean, we perceive that the two things cannot go together, okay? If the first is true, the second cannot be true at the same time. Of course, there are borders for this, and this makes the task difficult, okay? So because, as I mentioned at the beginning, this is a probabilistic relation. Another extension is that it's not just that there are entailment and not entailment. In the not entailment side, you can distinguish between contradiction, like this case, and unknown. The two portions of text actually talk about different topics, different things. And during the years, there has been RT systems which have been tested on these tasks. Another possible extension is partial entailment. This happens quite often. So you have one sentence, and just a portion of this sentence are entailed by another sentence. Okay? So this partial entailment has been proposed by Rodney Nielsen in the context of student answer assessment. Okay, so this is just to give initial initial background on semantic inferences. Let's talk about the technology, what we have today in this area. So, as I mentioned, the main initiative has been recognizing textual entailment. Started 2005, supported by Microsoft Research for several years, supported by one European project, one European network of excellence called Pascal. NIST, the National Institute for Standard and Technology in the States, has been involved in the organization. There has been publications. The results, the best result in 2012 for a system recognizing textual entailment is 73% of accuracy, just a yes-no decision. There is entailment, there is no entailment. Okay? So basically, this is a very good system, but the average of the systems participating in this edition of the competition was 61%. Okay, so you see that there is still a lot of work to do. I will mention about the software available in a moment. Now we have this platform, Excitement platform, which perform textual inferences. If you want additional information, there is a wiki website where you can find all the data sets, all the results, and I mean the story of this initiative. One interesting aspect in this competition is that differently from previous approaches where you needed to build logical forms, in this framework, the dominant approach is based on machine learning. Basically, the idea is that the system tried to learn as much as possible from the annotated data set. So you have pairs, text 1, text 2, text hypothesis, annotated with the correct relation, entailment, not entailment. The system tried to learn as much as possible, build a model, and then apply the model on new pairs. Okay, this is the global strategy. And actually, most of the system build a vector of features and then compare the vectors in order to take the decision whether there is entailment or not entailment. And the features which are used usually are very simple features, okay? Like a lexical feature, or similarity feature, the fact that let's say in the first text there is a word like home, in the second there is a word like habitation, and that in WordNet these two words are considered as synonyms. Okay, so this is a kind of feature that the system uses. So there has been several initiatives also for cross-lingual textual entailment. Recently there has been an initiative called SIC at Semeval 2014, this year, where people tried to judge similarity and entailment in pairs which have been constructed with distributional similarity purposes. Which are the needs in this area, at least in my opinion? So there are no shared practices on textual entailment. So for instance, it's very difficult to reproduce an experiment done by someone. If I want to reuse the same data, the same algorithm, and I want to reproduce this experiment, is almost impossible. It's very, very difficult. This also, as a consequence on evaluation, is difficult to compare. If it is difficult to compare and to reproduce things, it's difficult also to evaluate the progresses. So what we think in this excitement project is that there is a need for a shared platform where people can easily reproduce experiment, so that I can easily say and easily compare my system with others. So now I will briefly introduce this open platform for textual inferences. So there are a number of high-level architectural decisions that we have been taking. So the first decision is that on one side we have the linguistic analysis. We have the two texts, text 1, text 2, remember, which is the input of the platform, okay, the raw data. First, we want to analyze this text. And we know that we have a lot of pipelines doing tokenization, part-of-speech tagging, lemmatization, named entity recognition, dependency parsing, and so on. Okay, so on one side we have all the linguistic stuff. We call linguistic analysis pipeline. On the other side, we have algorithms which are based on top of this data and which decide whether there is entailment or not. Okay, so for instance, one algorithm could try to measure the distance between the first text and the second text. If the distance is below a certain threshold, the algorithm could say, yes, there is entailment. If the distance is above this threshold, the algorithm will say, no, there is no entailment. But the first decision is to clearly separate linguistic pipeline, linguistic annotation from the algorithms which take the entailment decision. You can find more about this in the Excitement website. Okay, this is this Excitement open platform. So if you download it today, you get these things. Okay, so just in few words, the input to text, like smoking causes lung cancer, and you want to check whether this sentence entails smoke hurts your lungs. Okay? So you want to know whether there is an entailment relation between these two portions of text. As I mentioned, first, the input is given to the linguistic pipeline. Okay? Now we have pipelines for 3 languages, Italian, German, and English. It's still quite simple, basic pipelines. Tokenization, part-of-speech tagging, lemmatization, named entities. For English, we have dependency parsing. But it's quite things that you can find quite easily. Everything then, the result of the pipeline is represented with WIMA. You know, WIMA is a kind of general framework for representing text and several layers of information in text, which has been developed by IBM. It's open, so we decided to use WIMA because this make our pipeline, our platform compatible with many other tools around. Then, as I mentioned, we have algorithms. Okay? In this moment, we have a number of algorithms like edit distance, classification algorithms, transformation-based algorithms, alignment-based algorithms. These algorithms address the textual entailment problem with slightly different perspectives. So in distance, the algorithm measures a distance between the first text and the second text. In transformation, the algorithm tries to transform each portion, each word in the first text into words of the second text. And for each transformation, there is a cost associated. With alignment, the algorithms try to establish semantic alignments between portions of text. These operations are carried on by what we call components. Each component is responsible for a single operation, very well defined. And components, like lexical components, may use resources, like a WordNet for several languages, like Wikipedia, for instance. A lot of information is in Wikipedia. If I want to know that Trento, my town, is in Italy, this information is not in WordNet. I need an encyclopedia, like Wikipedia, okay? All this and many other associations among words may be found according to distributional similarity methods that make use of corpora. All of these different resources are processed as entailment rules. Okay, so we have a very standard, one single standard interface for all different resources. That's very important. Make it very easy to plug in a new resource which is considered as a source for entailment rules. I don't have time to explain all the architecture of this platform, but just to give an idea of, if you download today the platform, you get these things. Of course, this is open, so we hope that in the future, other resources, other languages, other components can be added to this platform. In fact, one of the main concepts of the platform is interoperability. Okay, I mentioned WIMA. WIMA guarantees such a level of interoperability among different pipelines. And we have several levels of interoperability so that you can interoperate different components, different algorithms, different resources, different pipelines. So there are different blocks, and you can actually compose your entailment engine using several configurations of the building blocks. So this was a quite important thing. This configurator at the beginning allows you to configure your experiment, saying, I want to use this pipeline with this algorithm, this resource. You just select the things that you want to use, and you run your experiment. In addition, the platform comes with a demo, tutorial. We have an help desk. We have what we call the results archive. All the results that you want to store are shared with all the users of the platform. You remember one of the needs was, I want to reproduce experiments done by other people, okay? This is very easy with the platform, because you can download an experiment, exactly the configuration and the resources, the algorithm used by the person who did the experiment. So you can easily reproduce it. As I mentioned, this platform we call the EOP, Excitement Open Platform, is open source, GPL 3, so it's compatible with many resources and tools that are available to the computational linguistic community, including resources like WordNet, Wikipedia. I mentioned WIMA. OpenNLP is compatible with GPL3. Of course, there are resources which are not compatible with GPL3. So, for instance, GermanNet, the German version of WordNet, it's a proprietary license. Okay, so you have to ask to the people and so on. So this, for few resources, we cannot distribute it. So it's up to the user to get them. So if you want to know more about this platform, there is a website. This is the GitHub repository. And through this website, you can download the platform, install it, and everything. And there is a very good documentation. Okay, now I would like to address the third topic of the talk. It's entailment graph. So up to now, we have kind of, let's say, basic technology for textual entailment, which means I have a pair, text 1, text 2. I give it as input, and I expect yes or no, yes entailment, no non-entailment. Okay, and the open platform, the Excitement open platform, is a kind of entailment engine exactly doing this job. So in this case, we have independent pairs. Okay, I give one task. Every task is just one pair and one judgment. But all the pairs are independent. This is a kind of strong constraint which does not apply in many real, concrete scenarios. In many scenarios, we have dependencies among the pairs. Okay? So we need to address this issue. The initial motivation for that was actually text exploration. Okay? So you have a document archive, and you want to extract relevant knowledge according to some application, and you want to organize this knowledge in a very compact and efficient way. So the idea is to organize these pieces of knowledge, of relevant knowledge that you extract from document in a graph structure. Okay? Then once you have this graph-based structure, you can navigate the graph. In this idea, the nodes of the graph are a portion of text. Let's call them statements, a sentence with a predicate and the argument of the predicate and modifiers. Okay? Each node is a statement, and the relation among the nodes is entailment. So the goal, the long-term goal is to guide the user through the facts that are present in a certain domain. You can imagine a system which is able to automatically extract the statements and organize the statement in a graph. Okay? And this is the relevant knowledge that you have in a big archive. Today, what we have today? Today we have kind of technology which is able to organize such knowledge in terms of concepts or categories. Okay? Usually each document is classified into one category. Okay? So this document is about football player. Okay? This document is about volley. This document is about basket. And then you reconstruct a kind of taxonomy of these categories, labels. This is the typical technology which is available also for companies, many companies. Our goal is to move from the concept level to the statement level. So it's not just basketball or volley, but a statement like this team won against this team. Okay, so much more fine-grained information. A statement, I remind, is a predicate with the arguments. Okay, so typically a short sentence. So The idea is that moving from concepts to statements, we can manage much more fine-grained knowledge about a certain domain. Actually, it is at the level of the proposition, at the level of statements, that we communicate information. Okay? So it's much more natural to have as an atomic portion of text propositions, statements, instead of concepts. So you may also think about these entailment graphs as a kind of alternative to knowledge representation. Okay? In knowledge representation, you have ontologies, knowledge bases, where you have taxonomies of concepts. Now we are proposing something a little similar in the spirit, but where portion of text is the content of the nodes. Okay? And again, this is very useful for information exploration. It's useful for summarize the knowledge that we have in big repositories. So in some sense, this is something similar to, let's say, other approaches like Freebase, Google Knowledge Graph, the kind of ontologies we have in the semantic web. But this time, the spirit is much more closer to the information extraction spirit, in particular to open information extraction. You know that in open information extraction, people collect a lot, huge amounts of, let's say, triples. Okay? So these triples actually do correspond to small portion of text, statements. So the idea is, why don't we organize these statements, these triples, in a taxonomic way using the entailment relation? What we can gain with respect to open information extraction is that in open information extraction we don't have canonical forms. We do not know whether when two triples actually means the same thing. Maybe that they are just different because the language allows variability, but their meaning is the same. What we want to do is to discover these relations and organize them in the entailment graph structure. Okay, so as a first step, we want to define statement entailment graphs. The nodes are statements, atomic natural language propositions, and with the predicates, the arguments, and the modifiers, and the edges are entailment relations. This is a kind of example of what we have in mind for entailment graphs. Okay? So you see, for instance, that in each node we may have one or more statement. When we have two statements in the same node, the assumption is that they are one, the paraphrase of the other, okay? Bidirectional entailment. So if I say penicillin cure pneumonia, this is a paraphrase of penicillin treat pneumonia. And these two entails the fact that penicillin relieve cold. Okay? So this is the entailment relation, and when you have more than one statement within a node, they are considered as synonyms. So what you have to image is a system which is able to automatically extract these statements from, let's say, huge archives of documents and automatically organize them in this kind of representation. You see, maybe it's very small, but you see that the typical way is to, annotate this statement with the syntactic, the dependency information given by the syntactic structure. So, for instance, penicillin is the subject of the predicate cure, whose object is pneumonia. Okay, so One important thing in the definition of the entailment graph is that we need to take into consideration the transitivity of the entailment relation. In fact, if A entails B and B entails C, we can infer that A entails C. Okay? So an entailment graph, under this perspective, should preserve the transitivity of the entailment relation. This is important because, as I mentioned at the beginning, it's not just that we have many different pairs and we establish the entailment relation in isolation. At the very end, we need to compute the global transitivity of this graph. Okay? So we need global methods for the optimization of the transitivity relation in the graph. One of the initial work on entailment graphs, which have been applied to automatically collect entailment rules into graph, is this one, Berant et al. At ACL 2011. This is another example. This was brought very recently in a workshop on semantic parsing this year in Baltimore, a workshop at the ACL conference, where Mark Steedman actually presented a very interesting idea. So he says, I am a logician. My view is that the lexicon for a natural language system has to be based on formulas, basically. Okay, but I have to admit that I have to manually provide this lexicon. So one nice idea is that this lexicon actually can be automatically constructed based on the entailment graph idea. So, for instance, this is the enter for the verb conquer, okay? And you see arg0, arg1. This verb actually entails the invade verb. So every time we conquer something, we invade that something, okay? So this is a kind of entailment-based, graph-based representation of the lexicon for a parser, okay? And this has been experimented by Steedman and his students very, very recently. So just to conclude this short introduction to entailment graph, we see quite a lot of potential in this idea. So first, while the RTE systems, the RTE framework, just considered pairs, text 1, text 2 in isolation, now we have a way for considering their dependencies, which is very important. These entailment graphs can be seen as a kind of knowledge, a kind of formalism for representing knowledge about a certain domain, and for organizing the knowledge of a certain domain. This time, the basic, the atomic entities are statements, not concepts like in an ontology, but statements. So there is a kind of difference between this idea and formal representation of the knowledge. It's very interesting to think about entailment graphs as for their possibility to be integrated into discourse-style relationships. For instance, temporal relation, causal relation. So, of course, this entailment relation does not capture everything about the meaning of a text, okay? There are many other relations. So the idea is to, for future research, is to try to integrate the entailment relation with other, let's call them pragmatic relations, like the temporal and causal relations. Okay, so now the last part of the talk. In this part, I will give something more concrete. So how in the excitement project we try to apply the entailment graph idea to a very specific industrial scenario. As you know, in the European project, we need the industries. And in this case, we have three companies, one from Israel, one from Italy, one from Germany. And all of them are interested, are active in the area of customer interaction. So the scenario is like this. There are customers who calls in several ways a call center, okay? So, and they usually, they complain about some service, okay? So this is just an example of a few interactions. So an interaction is part of a call, okay? Like the first one, efficient service, quick through security and check-in. Staff could have been a bit more friendly, and the leg room in standard class was quite poor. Okay, so this is a person calling a call center and giving recommendations or complaining for the service the person has received. As you say, in this interaction there are parts which are of interest for the manager of a call center and other parts which are less interesting. So in this case, for instance, it's very interesting that leg room in standard class was quite poor. This piece of information is important because it's a clear complaint about the service. So in the project, we had a number of high-level requirements, user requirements, so-called. Okay, so the industry they would like to have compact and informative representation for these complaints. They need to manage streams of data. Okay, so every day, every hour, new data are coming. There are multiple channels: emails, speech, social media. And there are also multiple languages, in our case, English, Italian, and German. And what we proposed to the companies is to use as a core technology the entailment graph. And this, the construction, the automatic construction of the entailment graphs, starting from the interaction, has to be based on the EOP platform I have talked about in a few minutes ago. Okay? So basically the idea is the following. We start with a stream of data, like this statement. Disgusting coffee is served. No vegetarian food. Sandwiches are overpriced. They have horrible coffee. Journey is too slow, and blah, blah, blah. So imagine that you are able to extract this statement, this piece of information. Everything is complaining. People complain about everything, okay? So imagine you have this stream of data. Every hour, new of these statements are coming. The idea is that we want to reorganize them in a better way. Okay. So when we have a similar thing, statements saying with the same meaning, we want to group them in the same node. Okay. Sandwiches are too expensive. Sandwiches are overpriced. You charge too much for sandwiches. They have the same meaning. At least they have the same meaning for the people working in this call center, okay? Maybe a linguist could argue that the meaning is different, but for the purposes of the call center, they have the same meaning, right? So we want to collect all of them. This is kind of paraphrasing, okay? But then we want to link them, to associate them to a more general complaint, like food on train is too expensive, okay? Or not happy with the catering, okay? So basically, the more specific entails the more general, right? That's the idea. So the idea is to automatically build this kind of this kind of representation. So now the question is how far we are from this, okay? Which performance can be obtained using the state-of-art technology? How we can do it? And this is the rest of the final part of my talk. So let me give you an idea of the main steps for building these entailment graphs. Okay, the first step is that we want to extract this statement. Okay, now I show you this. I show you these statements already there. Okay, but actually we want to extract them. Okay, this is the first thing. We don't have them. Okay, because they are included in longer interactions. So the first step is to extract them. The second step, it's important. In the first step, we want to extract them and we want to annotate this statement. Particularly, what is very important is to annotate the modifiers. These statements are made of predicate, the main verb, arguments, object, subject, object, and possibly modifiers. Legroom in standard class. Okay, in first class, standard class, it's a modifier. Okay, we need to annotate modifiers. The second step is that we want to build an entailment graph for a single statement. Okay, statement with a modifier. So we want to decompose the statement. I will show you an example and build one graph for a statement. The third step is what we call the merging. Now we have a lot of small entailment graph, each for a statement. Then we want to merge them, okay, when possible. So the last step is merging the entailment graphs for different statements. Check the global consistency. Remind that we have this problem of maintaining the transitivity relation, okay? And the output will be one merged graph. So let me go through an example. So you remember our first interaction, efficient service, blah, blah, blah. Remind that we are interested, not we, our call center, the manager of the call center, our user, is interested in motivations for complaining. This is what they want, okay? So we need to automatically extract from the first interaction, staff could have been a bit more friendly. This is a complaining. And the second is legroom in standard class was quite poor, okay? We want to extract these two fragments, okay? Okay, so we start from the interaction. We extract one fragment. Legroom in standard class was quite poor. I told you that this has to be annotated with the modifiers. In this case, we have two modifiers. In standard class is a modifier of the predicate of the legroom, and quite is also another modifier. How can we automatically detect modifiers? The easier things to try is to use a dependency parser and to detect all the modification relations. Of course, this does not work for all the cases. Once we have this, we remove one modifier at a time. Okay, so for instance, in this case, we remove in standard class. What we have is legroom was quite poor. In this other node, we remove quite. Legroom in standard class was poor. In the last one, we remove all the modifiers. Legroom was poor. Okay? So this means that we decompose the initial statement, removing one at a time, all the modifiers. Why we do that? We do that because imagine one person, another customer, who says legroom was poor. We need then to merge the new statement from the new customer with this one, which were not possible if everything is in the same node. Okay? So we want to have as much as possible of the connections. Then we build the entailment graph. It's very straightforward for one single statement. And the last phase is that suppose that there is another customer saying not enough legroom. We want to take this piece of text, this fragment, and merge it with this one. Legroom was poor. You see why we have decomposed. Would not have been possible to merge this statement with the initial node. At the end, we have the merged graph. Okay? In the merged graph, legroom was poor, and not enough legroom, pronounced by two different customers in different moments, now are in the same node. Okay? Okay, so this is the basic procedure. 5 minutes. Okay, I'm concluding with the results. Okay, so now we have two activities in the project. One is we want to build a gold standard, a data set for where we have this entailment graph manually constructed. Okay, this is going to be the reference for our experiments, for evaluation. One activity. The second activity, we want to automatize these 3 steps of the procedure and calculate the results, again the gold standard. Okay? So I will present one slide about the gold standard and one slide about the results. So this is about the gold standard. Okay? So now this gold standard is a set of data. It's available for 3 languages. Now I have the results for 2 because the German one is a little bit different, for English and Italian. For English, we have speech and email. For Italian, we have speech and social media. This is the number of interactions. You remember what is an interaction? Okay, so more or less 350 interactions for English and the same for Italian. From these interactions, people, annotators, have manually extracted a number of fragments of statements. You remember the nodes of the, and each statement has been manually divided in sub-statements, and this is the size of the final graph, resulting number of nodes and number of edges. Okay. We have to consider a few data about these data sets. There are a lot of negative edges, much more negative edges than positive. We can imagine it because you have to compare each possible pairs of the statements. The majority of them do not have entailment relation, so they are negative edges. No entailment. Just a few of them have positive edges, positive entailment. We have calculated the agreement among different annotators. This is a kind of quite difficult task, okay? And there are one step which is agreement on the modifiers. Okay? In this data set, also the modifiers of each statement have been annotated. So we have a kappa of 78 for English, for the agreement of the modifiers, and we have kappa 66, which is still reasonable given the complexity of the task, for the graph, for the whole graph. So this number says how much 2 different persons agree on building the same graph, given all the statements, all the different statements. Okay? These data have been anonymized, so in place of the real name of a service or the real name of a company, now we have placeholders. And these data sets are available through the Excitement website. Okay? So this is just an example of what you can find in this data. So there are clusters of graphs according to different services, like the website of the company, facilities, and so on. I want to move now to the automatic part. Okay, now we have this data set, and we can compare our results against the data set. So we have a procedure, we have an architecture for automatically performing all the steps. And these are the very, very initial results, okay? We consider them as a kind of baseline, okay? So for instance, in this experiment, the training has been done on RT data. The test has been done on the entailment graph we have manually constructed. We have been using a generic algorithm, no attempt to optimize the algorithm on the domain data. You can imagine that we are talking about very specific services. We have been using Beauty, one algorithm, just two resources, WordNet and the Verb Ocean. There are no specific lexical resources for the domain, although we can imagine of doing that. And these results are divided in three parts. The initial is how much the algorithm is able to build, to judge each single pairs. The transitive, what happens when we add the transitive closures, what happens when we add the clicks. Okay, so now our baseline is 55% F1 measure. We consider this as a baseline for further research. Okay, just to conclude, I've been talking about textual entailment, particularly about entailment graph. Two things I think are important. One, as a result of this excitement project, now we have an open source platform. There's been quite a lot of work engineering work for developing this platform. And then we have a nice application scenario, customer interaction. And in this scenario, we have data sets that people can use, and we have a baseline for further research. Thank you very much.
So thank you for interesting and stimulating talk. And because time is basically out, we have just time for one short question.
So it seems to me that the domain that you chose for experiments, the complaints domain, is quite tricky, because I think that when people complain, they use irony a lot. So for example, somebody may say, okay, so 30 centimeters is enough leg space, sure. And then have you come across it, and have you thought about how to handle it?
Yeah, we know that there are a number of phenomena which are quite specific of the domain. All of these specific phenomena we call pragmatics of the domain. For instance, one very typical thing, if you complain about something, then this entails that you would like this something, okay? So if you complain about leg rooms, it's usually because there is not enough. And so you would like to have leg rooms, okay? So these entailment rules, I complain about something, I would like something. This rule holds in this domain, but does not hold for other domains, okay? And I mean, irony, it's for sure a big issue that I don't have answer for you for the moment.
So thank you very much once more.
Thank you very much.